Welcome back to The Explainer. Today, we're diving into the hidden anatomy of industrial connections. We're going to look past those massive tanks and towering structures to focus on something much more fundamental, yet absolutely critical for a plant to actually work. Seriously, think about it for a second. How do you connect the massive steel veins of an industrial plant without a single leak? How on earth do engineers keep incredibly hazardous, high-pressure or scorching hot materials flowing safely, day in and day out? Well, that flawless operation, it definitely doesn't happen by accident. It's all about incredibly precise engineering. So, here's our roadmap for today. We're going to look at the lifelines of industrial plants, understand pipe schedules, figure out how we connect pieces with flanges, break down flange ratings and faces, and finally, seal the deal with gaskets. Let's get right to it.
The lifelines of industrial plants.
All right, let's dive into the absolute foundation of fluid transport, the pipes themselves. Now, if you're new to this, you might just picture a pipe as, a simple hollow tube moving liquid from point A to point B. But in plant engineering, pipes are basically massive, heavy-duty Lego blocks. They are highly specific structural components. We're talking about pieces built directly into multi-million-dollar equipment as nozzle necks. Sometimes really large diameter pipes are actually used as the bodies of small vessels themselves. They are the absolute foundation and the universal language for piping teams worldwide.
Understanding pipe schedules.
So, since these pipes are so incredibly versatile, how do we actually size them? To do that, we really need to demystify a term you're going to hear constantly in engineering, the pipe schedule. Take a look at this standard specification table. Notice something interesting at the top left? The outer diameter, or D, is fixed at exactly 168.3 millimeters. That number stays locked in, it doesn't change whatsoever. But as you look down the schedule column, going from 5S up to 160 in XXS, the thickness numbers progressively increase. And because of that, the inside diameter gets smaller.
This perfectly illustrates a core engineering principle. Increasing the schedule literally just means increasing the wall thickness of the pipe to handle much more extreme internal pressures. But, and this is key, the outside diameter is completely untouched. Why does that matter? So it always fits perfectly into standard external connections and supports. A higher schedule gives you a thicker, stronger wall with less space inside, while a lower schedule gives you a thinner wall and more room for standard flow. It's basically a perfect balancing act between strength and volume.
Connecting pieces with flanges. Okay, now that we've sized our steel veins, we need to talk about the joints. How do we securely attach these standard pipes to each other, or to some crazy expensive plant equipment? Enter the flange. Think of a flange as a specialized, flared connection point. It's the vital mechanical joint that lets us build out the plant piping system piece by piece. And the best part? Because it uses bolts instead of permanent welds, we can actually take it apart later to inspect, clean, and maintain the equipment over its decades-long lifespan. It's a real game changer. But there isn't just one type of flange. Depending on the environmental stress, engineers choose from 4 core types to make these connections secure: the welding neck, the slip-on, the long welding neck, and the blind flange. Let's compare them. First up, the welding neck versus the slip-on flange. The welding neck is exactly what it sounds like. It has a long, tapered neck that's butt welded straight to the end of the pipe. It is incredibly robust, giving you maximum strength for high pressure or extreme temperature situations. On the flip side, the slip-on flange literally slides over the outside of the pipe before being welded. It's much easier to install, which makes it highly convenient. But actually, scratch that. It's strictly reserved for lower pressure situations where you just don't need that massive heavy-duty durability. Next, we've got the long welding neck and the blind flange. Out in a plant, equipment is often wrapped in thick layers of insulation. A standard flange would just get completely buried in that stuff. So, the long welding neck acts like an extended arm reaching right through the thick insulation to give us a clear, accessible connection point. Conversely, a blind flange isn't connecting a pipe to another pipe at all. It's actually a solid steel plate used to securely cap and seal the end of a line. Think of it as the ultimate stopping point in the system. The whole shebang just stops right there. Flange ratings and faces. Now, choosing the shape of the flange is really only half the battle. We also have to factor in the intense pressures of an industrial plant. So the absolute crucial point here is understanding the flange rating. You'll often hear engineers throw around terms like Class 150 or Class 300. This rating isn't just a random number. It's a rock-solid guarantee of safety. It dictates the maximum allowable pressure, but the metal can safely handle at a specific operating temperature. You see, higher temperatures physically weaken metal. So the hotter the fluid inside the pipe, the less pressure a specific rating can safely hold.
And where does all that high-pressure interaction actually happen? Right on the flange face. This is the precisely machined surface area where the two metal connections literally meet face-to-face and get bolted and compressed together with immense force. Getting this face perfectly machined is absolutely critical, and it sets us up perfectly for our final mechanical component.
Sealing the deal with gaskets. Here's the thing. Even with perfectly machined flange faces bolted together, microscopic gaps will always remain. And fluid under extreme pressure, it will inevitably find those gaps. So we have to seal the deal with gaskets. Now, if you look at piping blueprints, you might see a raw engineering specification string exactly like this one. To a beginner, yeah, it looks like an intimidating secret language. But don't worry, we're going to decode this exact string together into plain English. Let's break this down line by line. Step 1, CL 150. This simply means the gasket matches the class 150 pressure rating of the flange it sits in. Easy enough, right? Step 2, 316SS spiral wound graphite. This is the active sealing part. It uses a strong stainless steel 316 metal strip wound tightly in a spiral, which is then filled with soft graphite. Step 3, I-ring 316SS, O-ring CS. This just tells us it has an inner ring made of stainless steel and an outer ring made of carbon steel. When you put all that together, you get the perfect seal. The inner and outer rings perfectly center the gasket and hold the entire assembly securely in place, stopping it from buckling inward or blowing outward under extreme pressure. The metal spiral strips provide the raw structural strength to withstand the internal plant pressure, while that soft graphite filler compresses deeply into those microscopic imperfections on the flange face, actively blocking the fluid. It's literally engineered harmony. And that harmony is exactly what keeps our modern industrial world running safely. As we wrap up this explainer, I want you to remember why all this matters. The safety of a multi-million-dollar plant, the protection of the surrounding environment, and most importantly, the lives of the workers inside. They all rely entirely on these fundamental connections working flawlessly. From the precise schedule of the pipe, to the shape of the flange, down to the intricate material layers of the gasket, every single detail matters. So I'll leave you with this. Next time you look at a massive industrial piping system, will you just see a simple metal tube, or will you see the hidden, perfect engineering of a flawless connection? Thanks for joining me on The Explainers, and I'll catch you next time.